There we go. And you have a quiz, the most important part of it, on 2.1 through 2.3 on Friday in class. Don't miss it. Okay. You can have a sheet of paper with notes. You can use a calculator. Same quote unquote rules apply. Okay. In class on Monday, I handed out a worksheet. If you're here today and we're not here Monday, I have copies. If you weren't here Monday and you're not here today, that's okay. You can go on to Moodle and get a copy of it. One of the other things that you're going to see on Moodle is I have the solutions posted. Okay, I didn't do that immediately, but I do have them posted, but I'm happy to answer questions on the worksheet as well. Okay, so please be aware of this. I mean, this is especially to those of you who are listening to this recording because everyone else is here. Okay, questions on this stuff. Now I do have 2.4 that I intend to cover. And you know, maybe I can cover it before the quiz on Friday, or perhaps I can cover it in class today. It should only take us about 10 minutes or so. It's not on the quiz. You have about 5 homework problems associated with it. It's a really minor thing. It's more, I want to make you aware of these things rather than you're responsible for this sort of material in a college algebra class. Cool? Awesome. All right. So suppose you're given this information and you want to find the equation of the line. Okay. The first thing we need to do is write each of these as ordered pairs. How do I write this first bit of information as an ordered pair? Be careful. Other way. -5, -1. Good. Right? This is your input. That's your function value. And then this one is 2, 3. This question was asked of me outside of class, so I thought I'd start out class doing it. All right. When you have 2 points, what's your first thing to do if you want to find the equation of a line? Find the slope. Okay, remember, if we want to find the equation of a line, we need to find our value of m and we need to find our value of b. I want to point out you're not given your b value here. Okay, you know you're given your b value right from the get-go if it's of the form 0, something, right? Because by definition, your b value is your value of y when x is 0. So let's first find our slope. We have 3 minus a -1 over 2 minus a -5. If you have a question, stop me. Okay. Minus a negative is plus a positive. 3 plus 1 is 4, and 2 plus 5 is 7. Cool. All right. So thus far, we have this for the equation of our line. We now know that y is equal to 4/7 x plus b. Thing is, we got to find this value of b. Okay. We're not given the value of b, but notice we're given 2 values of x and y that fit on this line. Therefore, what we do is we take one of these ordered pairs, plug them in for x and y, and solve for b. Note, it doesn't matter whether I pick -5, -1, or 2, 3. There's infinitely many points on a line. So no matter which ordered pair on the line you plug in, you're gonna get the same value. Who should we plug in here? 2, 3. Okay, so if I plug in 2, 3, y is 2 when, or y is 3 when x is 2. Do as I do, not as I say. Never said that to my kids. You with me this far? Okay, so now we got to solve for B. So we get 3, well, this is 8/7 plus B, right? 4/7 times 2, multiply numerators, multiply denominators. And now in order to get B alone, what I need to do is subtract 8/7 from both sides. Okay, so what I need to solve is 3 minus 8/7. Well, what we should do is write 3 with the denominator of 7. Do you agree 3 is 21/7? And 21/7 minus 8/7 is 13/7. So the equation of this line is 4/7 x plus 13/7. Any questions? All right. Are there other questions people want me to go through right now? Yeah. 2.223, you bet. .2. Is it okay if I do my version? Okay. Kiki, I'll share my screen in a second. Oh, cool. We get to talk about moose. Hooray. All right. So here we go. So I'm going to write down the relevant information on this sheet of paper, and then I'll stop sharing my screen so you can see my sheet of paper. So we're told that in 1993, the moose population was 3,240. And in 1996, it was measured to be 3,870. Notice we're assuming that the population changes linearly. So we're going to want to find the equation of a line, i.e. find our slope and intercept. And notice that they tell us how they want T to be defined. T is the number of years since 1990. You okay this far? Awesome. All right. So we're given some information. We want to find the equation of a line. What we need to do is take this information and translate it to ordered pairs. Notice my input is my time, the number of years since 1990, and my output is my population. Okay, so how would I take this first piece of information and write it as an ordered pair? Okay, well, if T is the number of years since 1990, how many years after 1990 is 1993? 3 years. So my first ordered pair looks like this. And knowing that, then, how would we express 1996? 6 and then 3870. You get this far? Okay. How T is defined is very crucial. Okay. Yeah. All right. Do you want me to take it to completion? Okay. What's my first job? Find the slope. My slope is the change in Y values over the change in X values, even though they're P values and T values. All right, so 3870 minus 3240 is 630 over 3. So we get M to be 210. So now we've gotten this far. You with me there? Okay, well, how do we find our value of B? Again, we take one of these ordered pairs and we plug it in. Why don't we take this first one and plug it in? So my population is 3,240, 3 years after 1990. And I'm just going to be lazy here and use a calculator. To solve this, we subtract 630 from both sides. So we're going to get B to be 2610. So this tells me that the formula for my population is this. Now, I seem to recall that there was another part, but even aside from this other part, I want us to interpret this. What does this 210 mean? Yep. On average, the moose population is growing by 210 mice per year. What is this 2,610? Beautiful. Isn't this my population when t equals 0? And when t equals 0, we're talking about 1990. So this is our moose population in the year 1990. Not that we were asked, but I think interpreting these things is really important. So from there was another part. I don't want to shortchange you here. It says, what does your model predict the moose population to be in 2009? Well, if we want to find our population, we better be given T. What is our value of T in the year 2009? 19. So we would compute P of 19. And I'll let you do that, but does that make sense? Thank you for asking questions. I appreciate it. Are there other questions? All right. Are there questions? Have y'all had a chance to look at the worksheet? No? Okay. Cool. So what I'm going to do right now is I'm going to talk to you about 2.4 so we can get that out of the way. And honestly, the quiz is not meant to take all period on Friday. So if you have any worksheet questions, I'm happy to answer them. But I am going to go do something really quick. So just give me 1 second. I'm just going to go to the Moodle page first. No. But it'll help you on the quiz. So in that sense, it's a good idea. And because what else would you rather be doing than that? Where to begin, huh? Yeah. Don't worry, I'm an extremely sarcastic human being. Okay. So now I'll share my screen so that the Zoomers can see. All right. So here is our Moodle page. We don't go here too often. But if you go to this class activities and projects, here is the chapter 2 worksheet. Right here are the solutions. Do not look at the solutions until you have tried the worksheet, right? Because it does not help you to know what the answer is beforehand, because then you know what to work toward. It's much easier to follow work than it is to create it on your own. Okay, so here's the worksheet in case you want to see it. Wow, look at all these other things that we have here. Oh, here's the review and here's the answer key to test 1. all these things. Cool. All right, so what I'm going to do right now is I'm going to talk to you about section 2.4. And with this section 2.4, again, what I want to say is that this is not on your test or your quiz. This is something that I take a lot more time and cover in my Math 115 class, but I will explain the motivation for it. Okay, so when we talk about modeling things linearly, in other words, what we want to do is take our data and find the equation of the line. Okay. The thing is, everything in a textbook fits very, very perfectly. Okay. But rarely does real life follow an exact linear model. Okay. In general, in real life, you might plot some data and you might say, well, it looks like it's linearly related, right? Like if this was our data here, do you agree it seems to follow the trend of a line? So what we would do then is say, well, what is the line that best approximates this data? Okay. So the whole point of this is no model, whether it's a linear model, an exponential model, a quadratic model, whatever, no model is perfect. Okay. And they get refined over time and they only tend to work for periods of time. Okay. Very rarely in real life does everything fit a perfect line. Okay. It just typically tends to follow a trend. So this data I could say is linearly related. It's not as tight of a line, is it? Okay, but we can still approximate it to get an overall idea of what that line looks like. Now, sometimes you might plot data and it looks like that. Okay, does that look like it's at all linearly associated? No, it just looks like a lot of different dots. It is the case that you can still find the line that best fits the data, but it's no line you're going to want to use to make any future predictions if you want to be accurate at all in the slightest. Okay, so given data, some fit a line very perfectly. That's the like 0.001% chance, but most kind of follows a trend. And as I mentioned, you know, you can follow other trends too. Like if I looked at this data, I would say this doesn't follow a linear model, but it sure looks like it follows an exponential model. Okay. So when we're talking about things in quote unquote real life, what we want to do is find the line that best fits that data. Okay. Now there's two things to it. A, what is the equation of that line? And B, just because you can find it, how can you tell whether or not it's a good fit? Because if it's a good fit, you don't mind making some future predictions off of that linear model. On the other hand, if it's not a good fit, you want to be like, I'm scrapping that model. Okay, so that's what this section is all about. And what I want to do is just mention a couple things to it. Okay, we use technology to find this. Okay, in no class do we do this by hand. And bless you, I'm happy to show you the formula if you want to see the formulas, and then you can be really glad that you never have to use it. Does anyone want to see them? Okay, so we had one person say no. So if you don't want to see it, don't look. Okay, but suppose this is your data. You don't have to write this down. You will never have to do this. I mean, honestly, in Math 115 and in Stat 216, this calculator takes care of it for us. Okay, so we have x1, y1, x2, y2, xn, yn. Suppose these are all of our data points and we have n of them. So to find the line that best fits the data, we need to find y equals mx plus b. And I'm going to talk about actually where it comes from in a second, but I'm just wanting to show you the formula so you'll be appreciative of technology. Okay, so to find the slope, what you do is you take the number of data points. Now this is a capital sigma. We use capital sigma to say that we're adding. And what we're adding is each x value times its corresponding y value. So x1 times y1 plus x2 times y2 plus x3 times y3 all the way down the line, minus the sum of all of your x values times the sum of all of your y values. And that's divided by the number of data points times the sum of all of your x values squared minus the sum of all of your x values squared. And to find your b value, you take the sum of all the y values minus the slope times the sum of all your x values, and you divide that by the number of data points. Now, do you see why, like, we just don't deal and why we're really thankful for technology? Now, what I want to say is as follows. The way the line is found, which those formulas don't do a really good job emphasizing, is this. Pretend that's the line that best fits the data. Okay, the way it's found is, number one, in case you care, it's called your regression line, or another term for it is your least squares line. That's where the squares came into our previous. Okay, so what is it? What you want to do is you want to find the line so that the difference between each data point and the corresponding point on the line, so these distances, are as small as possible. Okay, now why is it called the least squares line? Well, if you take this data point minus the point on the line, you're going to get a positive number. But if you take this data point minus the point on the line, you're going to get a negative number. And so the way that you deal with the positives and negatives so that they don't offset each other is you square everything. So essentially, you're finding the equation of the line so that the square of these distances is as small as possible. It makes you appreciate technology, I think, quite a bit. So one thing that I want to say to you is, a reasonable question is, how can you tell how good of a line it is? Okay, well, the way that you tell that is by something called the correlation coefficient. That's a value R. And I'm going to tell you some things about R. Okay, R takes on the sign of the slope. So if the slope of your line is positive, so is R. And in fact, R is between 0 and 1. If R equals 1, you have a perfectly fit line. If the slope of your line is negative, so is R. And in that case, R is between 0 and -1. And similarly, if R equals -1, you also have a perfectly fit line. It's just decreasing. And you don't need to memorize any of this stuff. Okay, the key is R is always between 1 and -1. R is called our correlation coefficient. That measures how good of a fit the line is to the data. And you don't want me to write out the formula for that. And I don't mean to tell you what you want and don't want. Heck yeah. So what I want to do is actually give you some specifics here. Okay, so these are our rules of thumb, but obviously they depend very much on the situation. Okay, so when you have a positive slope, if R is between 0 and 0.5, it means it's a bad fit, don't use it. If your correlation coefficient is between 0.5 and 0.8, you've got a moderate fit. So use it, but take note that it's not great. And if R is between 0.8 and 1, it's a good fit. You can use it with at least a certain degree of confidence. And the same thing follows with a negative slope. If R is between 0 and -0.5, don't use it. If R is between 0.5 and 0.8, again, it's a moderate fit. And if R is, if R is between -0.8 and -1, it's a good fit. All right, let me know when you have that written down. Okay. Can I share my screen? Let me first make sure I'm on what I want. So if I share with you section 2.4, I can show you the textbook. And I just want to walk you through this a little bit. Here they were modeling, and I recommend you read through this. I think it's kind of interesting. I mean, this is reality. But they talk about, like, here they're looking at cricket chirps in 15 seconds in the temperature, because it turns out that as temperature increases, so do the number of times crickets chirp. And they go on and on and on about it. And here's the correlation coefficient, which is always given to you when you compute the line. And they go through a bunch of different values. But what I really want to jump to, is this. I give you just 5 online homework questions. Okay. And I'm going to go through all 5 of them right now, not do them, but at least describe them to you so that this isn't something that you fret over. Cool. All right. So in this first one, literally what they want you to do is plot a bunch of points. So this is the first quiz, second quiz, okay? And we're looking at it for 8 students. So for example, this student got 14 on each quiz. So I would click the dot and then I would go to like 14 on my x-axis and 14 on my y-axis. And I would go doink. And then I would do that all along. Okay, so then I would do like 37, 37, 37, 37. Wow, those people are so consistent. It's amazing. Doink. Okay, so you're going to do this for all of them. And then what you're going to do once you have that plotted, all 8 ordered pairs plotted, is you're going to estimate the line that best fits it. So I would need to plot at least a couple more points to have any sort of idea of where it would be. And you get the point. Huh, get it? So if I was to draw the line that best fit the data, I mean, I would do something. I mean, this looks pretty darn good, doesn't it? Say, that looks really like that. Okay. You with me? Not much there. Okay. Now, what question number 2 shows you is how it looks when you actually would compute this in your calculator. Okay. So what this little story tells us is they wanted to know if there was a relationship between the number of hours TV watched per day and the number of sit-ups a person can do. Well, of course there is, because if you're watching TV, you can just sit and do sit-ups, right? If you're not watching TV, you don't have time to do sit-ups. Anyway, I'm just being stupid and sarcastic. Okay, but anyway, so what you do is you enter all these data lists in your calculator and you press the right buttons, and this is what it comes out with. So instead of MX plus B, a lot of calculators use AX plus B, but notice they give you the value of A and they give you the value of B. Okay, so if I was to write what the equation of this line is, given what we found, I would say Y equals what? Negative 0.689x plus 31.916. Okay. R squared is something you talk about a lot in the Stat 216 class. We don't really go into it here, but notice my R value is negative, which makes sense because my slope is negative. And it's 0.7, so we would say it's a moderate fit. Okay. All they want you to do here literally is plug 2.5 in for X and solve for Y. Right? In this case, they wanted to know how many sit-ups a person who watches 2.5 hours of TV. I just want to show you that this might look funky and intimidating, but it's really not. But I think it's super important to be aware of these things because, you know, we can model things in a textbook and it can look really good, but life ain't that great, which we know. Okay, so the next one has you play along with some correlation coefficients, okay? So what they want you to do is play match. Like this looks like a nearly perfect positive slope line, correct? Well, isn't that B? Remember, I gave you those ranges for the correlation coefficient, so I would put B here. Other one, well, do you agree that this looks like it's negatively correlated? And so does this one. I mean, they both look like mishmash. And we have 2 negatives. Which one follows more of a linear trend? the top one does. And therefore, you're going to pick the correlation coefficient that is better than the bottom one. Remember, the closer you are to 1 and -1, the better of a line you are. And then, of course, by process of elimination, we can say this one's A. In this one, what they do is they ask you to compare. Okay, so which one looks like it has a stronger relationship? 1 or 2? 1, totally, right? So you would click this. And finally, here again, you're just matching or selecting an answer. Does this have a positive correlation, a negative correlation, or no correlation? No correlation means it's gobbledygook. A positive correlation means that the slope of your line is positive. A negative correlation is the slope of your line is negative. Okay, so what are you going to tell me here? Negative. What are you going to tell me here? Yeah, no correlation. Gobbledygook. That's what they should have as a selection. And how about this one? Positive. A positive. Okay, so this is all the homework assignment is. And really, we don't typically teach this sort of stuff in a college algebra class, but I feel like it's dishonest to walk around pretending that everything fits things perfectly, because that's just not the case. Every model is wrong and every model is an estimate, and it has its limited uses for sure. All right, so I'm happy to still give you a week to do this assignment. Just don't forget to do it. I'm going to set the due date for it. And then give me just one more second here. Oh, come on. So a week from today is the 19th. Holy smokes. All right. There we go. So all of those have been assigned. And I'm going to write that down here. Here's my notes. 2.4. All right. So technically, we still have 10 minutes left. If anyone wants me to go through anything else, I'm very happy to do it. If you have any additional online homework questions in 2.1, 2.2, or 2.3, we certainly have 10 minutes left to do them. If you want a copy of the worksheet and run, there's the worksheet right there. You're welcome to take that. I'm happy to answer questions on it. What do you want? I can tell a few of you are like, go on, take the worksheet and run. You guys know Steve Miller Band? Okay. You wouldn't know by my singing. Do you have other questions? And let me put it this way. If some people just want to take the worksheet and run, take the worksheet and run. Like, I'm not at all offended if you're like, blue sky day, bye, Lauren. But I'm happy to stay here for another 10 minutes and answer math questions for those who want to hang out. Oh my gosh, you all have to state an opinion. Well, how about this? If you want the worksheet and then to skedaddle, here you go. I'll put it right over here. And I'm not at all offended, so don't even think twice about that. If you want to stay and ask questions, I'm standing right here. You just have to say the word. Thank you.
Oh, is test this Friday or next Friday?
The quiz is this Friday.
Oh.
Yeah, that's a great question.
Make it a week before two, like, problem.
Okay, 2.3, number 1. Let's look at it. Okay, do you mind that I use my numbers given? Okay. Yeah, I got to start at the very beginning at least. Oh, and actually I would do number 5 first anyway. Because immediately I would be like, oh, I want to find the equation of this line. Okay, so we are given, let me annotate here. So we're given that in 2003, the population is 2390, and in 2009, it's 3296. And notice again, they tell you that they want the formula to be given T years after 2000. So T is the number of years since 2000. Same thing, you're very consistent. That's good. That's good. Okay. So if T is the number of years since 2000, how would I write this first one as an ordered pair?
It gets me every time. Okay, so I answered it the first time, I just used them. It was in 2004 and then 1959, so I exported that with 0. But I still found the answer using doing it that way. Is that
Mm-hmm.
still correct?
Mm-hmm.
I would just.
Mm-hmm.
That basically answers.
Okay, cool. I'm glad I could help. Yeah, yeah. Anything else? Okay. Well, let me know if you have more questions. Kiki, do you have any questions? Or are you good?
I am good.
All right. Well, have a good